All right, so today we are going to start chapter 6, which is on trigonometry. So the first thing I usually do is just kind of throw the word up there and see if we can break down what it means, and then we'll go from there. Is there anything in the word trigonometry that people recognize? Like try. Yep, that means something. What does that mean? It means 3. All right, anything else there?
Metry.
Metry, yep, that means something. What does metry mean?
Like mathematics. Metric.
And what's that used for?
Arithmetic.
Measuring, yes. So that's measuring. Anything else there? Gone. Yeah, gone does mean something. What does?
Shape.
Something specific about shapes.
Size.
Sides, yeah. So really the idea of trigonometry is measuring a shape that has 3 sides, or measuring triangles. What do we measure? Usually angles and side lengths. So here's an example of something you could do with trig. Let's say that you have a building over there. You're standing over there with your arm detached. And let's say that you know how far you are from the building. Say you're standing 100 feet away. And you know that the building you're looking at is, 40 feet tall. And you want to know what angle you would have to aim something at, like maybe a laser pointer, to be pointed exactly at a target at the top of a building. All right? So that would be the question. What is that angle that you would have to point the laser at if the laser is on the ground to hit a target at the top of the building? Right? And we could figure that out based on the fact that's a right triangle, so that actually makes it a little bit easier. And what we would have to do here is use the measurements of this 3-sided shape that's in blue right there. So we have a triangle. So we're not going to solve that, but I'm just showing you that's an application of something you can do by measuring a shape that has 3 sides. Here's another one. Let's say that there's a boat. There's our boat. I usually do a little better. Usually comes out better. That one didn't. So there's our boat. And we have, let's say, 2 stationary people on land looking at the boat. We've got a person there. We got another person over here. And they're each looking at the boat. Now, let's say that it's like at night. So maybe the boat has a light on it. And they can see the light on the boat. And they're trying to triangulate or figure out exactly where the boat is. Maybe the boat needs help, and they're trying to send a helicopter out or whatever. They need to figure out exactly where the boat is based on what they can see. Well, if you know where each person is, all right, which that should be relatively easy. If you have a phone, you can just look up your coordinates, GPS, the other person looks up theirs. You can easily figure out how far apart you are. That's easy enough. So let's say that you're, 3 miles apart, you and the other person. And you each can see the light on the boat. So let's say when you look at the light, you see it coming in that direction. The problem is, if you're the only person that can see it, you can say what direction the boat is in from you. Like if you have a compass, or an app that's a compass, you can get the direction. But you don't know, is the boat a mile in that direction? Half a mile? 3/4 of a mile? 2 miles? You can't estimate a distance to the boat, especially if it's at night. You just might see a dot of light. But what helps you is this person can also see the boat. So now between the two of you, you have just created a triangle. And in that triangle, you know how far apart the two of you are, and you know the direction that you're looking in because you have a compass that tells you the angle that you're looking in. So you'd know this angle. Maybe it would be like 40 degrees, and this might be like 50 degrees. By knowing that two angles in the side, actually let me change that and make it like 55. You can figure out where the boat is. That's called triangulation. Triangulating someone's position based on two other people seeing that thing. What makes this a little harder though is this angle is not a right angle at the top. Right? Because 40 and 55, that adds to 95. If you subtract that from 180, that'll tell you what this other angle is. Because it's not a right triangle, we'd have to go about solving it a little different than the top one. Right? But it's still an application of measuring a shape with three sides. So what's nice about trig is a lot of it I can relate to something. Not every field, but there's a lot of things in trig that are less abstract than what we were doing in the algebra part. Like I could tie in triangles with carpentry. Like if you got a foundation and you want to make sure that when you pour it, it's exactly at a 90-degree angle, this is your foundation. To check if that's exactly a 90, you could measure 30 feet in that direction. You could measure 40 feet in that direction and mark those 2 points and measure the diagonal. If it comes out to 50, then you built something that's exactly a 90-degree angle. It's a 3, 4, 5 right triangle. I just extended it to be bigger, 30, 40, 50, for like the size of the house. Check a doorway the same way. It's all kinds of things you can do. All right, so that's basically what trig is. So even more basic than looking at a triangle, today we're going to talk about the angles within a triangle. All right. What makes up an angle? How do you measure it? Degrees is one way. There's a second method, and that's what we're going to learn part of today. So let's start with what is an angle. Well, that depends on how you draw the angle. Is it an angle inside of a shape, or is it an angle all by itself? I'm going to give you the definition of an angle all by itself, okay, not part of a shape. When you draw an angle all by itself, an angle is made up of two rays. When you draw an angle inside of a shape, like a triangle, it's made up of two line segments. But either way, where the two rays come together, that is called a vertex. Since an angle is made up of two rays, we call those two rays the sides, and each side has a name. One's called the initial side, and the other one is called, anyone have a guess what the other side is called? It's like a final ending, yeah, it's called terminal. So we have an initial side and a terminal side. How do you figure out which side is which? Well, if you draw two rays and you rotate between them counterclockwise, like this. Rotating between them. Where you start would be the initial, and where you end is the terminal. And it wouldn't matter how you turned that. If you did it like that, rotating counterclockwise. That's the initial. And that's the terminal. There's another example there. So when you're looking at an angle like that, you really have two angles. You have the one in between the rays. You also have the one on the outside. We're referring to the one inside, okay, when we talk about an angle. Initial, terminal. Any question on the names of the sides of your two rays? A lot of times we will not know an angle. In trig, when we don't know an angle, we're going to represent it with a Greek letter. Some books will use, like when we're studying triangles, some books will use capital letters for angles and lowercase letters for sides. I think that gets confusing because depending on what letter you use, it could look the same. Like a capital C and a lowercase c. Unless you have context of other letters, how do you tell if this is a capital C or a lowercase c? The other thing is, if I ask you a question like, find B, you'd have to be like, well, which B? The capital B or the lowercase b? Oh, sorry, I meant the capital B, not the lowercase b. It gets confusing. So we're going to stick with Greek letters for angles, English letters for sides. There are some of the Greek letters that we use. Does anybody know the name of the first one?
In physics, I don't.
Fish.
Kind of looks like a fish. Anybody else think they might know the name?
You don't like my name for it?
I don't know if that's the approved name in the alphabet. It's in the Greek
Greek
alphabet. It's alpha.
Oh.
Beta.
Alpha,
So
beta.
the first, yeah, the alpha, and then beta. What's the next one after beta?
Delta.
No,
No.
wait.
Nope.
It's a V.
How about that one? What is it? No, not sure. That is gamma.
It was
Oh.
okay. And I wasn't sure.
That one you use a lot in geometry.
That's theta.
Theta.
That's theta. And the last one?
Word.
That's the lowercase version of them. That's the capital version.
Oh, omega.
Omega.
Oh my god.
Yep. So not only do we use Greek letters for angles, generally they are all lowercase. And it's just a variable. Right? So when we don't know an angle, we pick a Greek letter. I'd say theta is probably the most common when you're talking about a single angle. When you need to talk about three angles at the same time, like in a triangle, alpha, beta, and gamma are the ones you generally use. Because they correspond very nicely with sides A, B, and C. Omega comes up in other contexts, but again, they're just variables. There is one Greek letter we would never use as a variable in math. Pi. Yeah. Don't ever use pi to represent an angle because pi already represents something else. Yeah. So, if I asked you to sketch a 90-degree angle, some people might do that. Other people might do this. They're both right. But what we would like is a way for everybody to sketch a 90-degree angle and have it with the same orientation. So that's where standard position comes in. So standard position is a way of drawing an angle so that everybody's angle looks the same. in standard position, two things have to happen. One, you need the initial side on the positive x-axis. Two, you need the vertex at the origin. So that is an angle in standard position, that red one. Okay. How about if I did this? Is that still standard position? No, what's wrong with that? So what doesn't make that standard position? Yeah?
The vertex isn't at the origin.
Vertex is not at the origin. Yep. How about if I did something like this? Is that standard position? No, what's wrong with it now?
So repeated.
Can you be more specific?
45 degrees.
No.
It's not on the positive x-axis.
What isn't on the positive x-axis? Right. The initial side is not on the positive x-axis. Okay. Vertex is at the origin, but the initial side isn't in the right spot. So standard position has to be exactly like that. Any questions on that? Okay. So degrees is one way we can measure an angle. It is not the most common way when you do pre-calculus and calculus. There is another way we do it. Well, let's start with degrees. How much is one complete rotation on a circle? How many degrees? 360. Now, yes, we are using 360 degrees to measure something, and we also use degrees to measure angles. This is different. We're measuring an amount of rotation. They both use the same unit, a degree. Okay? Whether you're in an angle, in a shape, or you're measuring movement on a circle. Now, you can rotate in two different directions. For now, we're just talking about counterclockwise. How about a half counterclockwise? That would be a 180. And a quarter?
90.
That would be 90. Yep. So if you rotate in the counterclockwise direction, you get a positive angle. What do you think would happen if you rotate in the clockwise direction?
Negative.
Right. So what we're doing there is the negative is representing direction. We'd never talk about negative angles inside of a shape. That doesn't happen. But when you are talking about rotation on a circle, since there are two ways you can rotate, we need a way to describe rotating the other way. So negative works perfect. All right, let's take a look at this. This is a program that lets me draw angles in standard position. Okay, I can move the terminal side, but I can't move the initial. And if I rotate in a counterclockwise direction, it gives me a positive angle. If I rotate and go back to 0 and then start going in clockwise, it gives me a negative angle. So that's the only difference between a positive and a negative angle. How do you read that top number? Negative 141 degrees. Does anybody know how you read the bottom number? Okay, that's what we're going to talk about. That is, by the end of today, you should be able to take that and turn it into the bottom number. I don't think I showed you that, but you can have more than 360 degrees when you're talking about rotation on a circle. All that would mean is you've gone around more than once. So there's 497. There's a bunch of angles. 2720. Okay. You just made more than one revolution. Now, going around more than once is fine, but it does make it kind of complicated to think about where the terminal side would be. If I gave you a terminal side, there's the initial. I think most people would be able to tell me the quadrant that the terminal side is going to be in if I keep the angle under 360. What if I said like 200 degrees? What quadrant would the terminal side be in?
I forgot which one.
Negative.
So the quadrant numbers are
3.
right there. 200 degrees? No, wouldn't be quadrant 1. Quadrant 1 is between 0 and 90. 3, yeah. So quadrant 3, if you drew an angle of 200 degrees, it might look something like that. How about an angle of 135 degrees?
Okay. 2.
Yeah, be somewhere like this. Terminal side would be in quadrant 2. How about 330 degrees? How much? Quadrant 4. Right? That'd be a very big angle, like that. All the 330 is almost all the way around. But if I gave you the angle 2,720 degrees, that's kind of hard to figure out what quadrant it's in. I mean, you can see it's in quadrant 3, but how would you know that? Well, we need to make that angle easier to work with. So let's do a smaller one. Let's do, okay, so here's 90. Here's 450. 90 and 450 basically land the terminal side in the same spot. Does anybody see, using arithmetic, how I can turn 450 into 90?
Just go back to 360.
Go back what?
360 degrees.
Yeah, go back 360 degrees, which means subtract. There you go. So 90 and 450 are exactly the same. Now, also, if I had a negative angle, we generally don't like to work with those because they're more complicated. How could I turn that negative angle into a positive one? Yeah.
By subtracting it from, well, adding it to 360 so that you get a positive amount.
Yeah, just add 360. So these angles, 90, 450, negative 270, negative 630, all of these angles are what we call coterminal. The idea of a coterminal angle is it has the same initial and terminal sides. And the easiest way to find angles that are coterminal is to add or subtract 360. When you are doing trig, coterminal angles will give you the same answers. Let me show you an example. We haven't studied all the trig functions yet, but we will by the end of the week. Let's say that I wanted to take and turn my calculator on. All right, so let's say I had to take an angle and find a trig function of it. So let's say I had to do the sine of 2,000 degrees. that's the answer that I get, negative 0.34. Now, there's an easier way to do that without having to work with an angle as big as 2,000. We could find an angle that is coterminal with it. So how could I take 2,000 degrees and make it a little bit smaller? I could subtract 360. So let's subtract 360, and we get 1640. Now, if I do the sine of 1640, how do you notice that answer compares to the one we just had? It's the same. Now, 1640 is still pretty big. So what could I do to make that even smaller?
Subtract 360 again.
Yeah, I could just keep subtracting 360 as many times as I want until I finally get an angle that I think is easy to work with. Let's try. All right, 200. 200 is a lot easier to work with. So now that's probably something I could do once I teach you a few things a lot easier. Okay? So if you type in sine of 200, you're going to get that negative 0.34 again. Okay? So that's the importance of coterminal angles. They give you something easier to work with, and when you're doing trig with it, you get the same answer. So am I saying that 920 and 560 are the same number? No. They're the same coterminal angle. Okay.
I don't get that.
No?
I get 187 radians.
So if you look at the top of your calculator where it says all those different words, I guarantee you the second to last word on yours is radians. Yeah.
Is there a way to change that out?
Yes.
Uh,
We'll talk about that. All right, so they want us to sketch an angle and then find one that's coterminal with it, that's positive and negative. Okay. So we're sketching it in standard position. So where is the initial side going to go? Can you be more specific?
The positive.
Positive x-axis. Yeah. No choice. Where would 30 degrees be? Which quadrant? Definitely one. Let's just kind of ballpark it. Is it closer to the y-axis, closer to the x-axis, or right in the middle?
Between the middle and the x-axis.
Yeah, it's closer to the x-axis. So that's probably a little too close, but that's the idea. So 30 degrees. And what would be an angle that is coterminal with 30 and positive?
390.
390. How about coterminal with 30 and negative?
Negative 330.
There you go. Any questions on that? Are those the only positive and negative coterminal ones? No, they're the first two though. Let's try this one, 145. Okay, what quadrant is 145 in? It's quadrant 2. Closer to the y-axis, closer to the x, or right in the middle?
Closer to the x.
It is closer to the x. 135 is right in the middle. Okay, so it's a little bit past the middle. So that's 145. And what would be an angle that is coterminal and positive with 145? 505, yeah. And how about an angle that is coterminal and negative? How would you find it if you're not sure? Yeah, just take 145 minus 360, negative 215. There's that one. And this one, negative 45. Where is the terminal side going to be this time? Start with the quadrant.
4.
Yep, quadrant 4. Closer to the x, closer to the y, or right in the middle? Yeah, anything that's a multiple of 45 splits it. Okay. 45, 135, 225, 315. Those are the positives. But negative 45 is, well, I actually just said what it's the same as. And we're going to write that down right now. So that's a 45-degree angle going clockwise. What's an angle that's coterminal with that? And positive. $315. And how about negative? Negative 405. Okay. So that's just a little practice finding positive and negative coterminal angles. Questions? Okay. Next, we're going to look at some names that you can use to describe an angle based on how big it is. First definition is going to be for an acute angle. How do you think you would define an acute angle? Yeah?
Anything less than 90? Well, any angle less than 90 between 0 and 90?
Yes, it has to be positive. Yeah. So, for example, a negative 10-degree angle, that's not acute. Okay, to be acute, it has to be between 0 and 90. Why not exactly 90?
Right.
Because that's a right angle. How about the next category, which is from 90 to 180? That's obtuse. And again, it does not include either the 90 or the 180, because when it's 180, what kind of angle do we call that? I didn't actually write this one on the board. That's a straight angle. Okay, so those first three definitions apply to a single angle.
Can you go up a little bit? Thank you.
The next definition applies to a pair of angles. Does anybody remember what you call a pair of angles that add up to 90? Yep. A linear pair would form a linear straight line. So a linear pair would be something like that, where angles 1 and 2 add up to a straight line. Yes, complementary. There's lots of terms here. It's easy to get confused. So it's two positive angles that add up to 90. Positive is important. So if you said like negative 10 and 100, no, those aren't complementary. Now there's another definition similar to this one that we usually talk about with complementary. Anybody know the other pair I'm thinking of? Yeah? Supplementary. And does anybody remember what those are? Can you be more specific?
All right, 2 positive to add 20.
Two positive angles that add to 180. So again, 190 and negative 10, not supplementary. That's because negative angles don't have complements or supplements. The complement is what makes it add up to 90. Supplement is what makes it add up to 180. Well, let's try finding some complements and supplements. Everybody have that?
No, I just need.
Just the bottom one? Okay. So let's find the complement and supplement of 48 degrees. Okay. Let's start with the complement. What is the complement of 48 degrees?
42.
42. All right. How about the supplement?
One hundred and fifty.
132. Yep. Any question on finding the complement and supplement? All right. How about the complement of negative 18? There is none. That doesn't apply. It's not applicable. Can't do it. How about the supplement of negative 18?
Also no.
Yeah, you don't, there are no complements and supplements for negative angles. Here, I'm going to give you a little more information. If you didn't know that, you may not necessarily have an answer. But x is an acute angle. What would be the complement of x degrees?
90 minus X.
Right, that's the most important concept to understand there. It's 90 minus x. That's how you find a complement. And the supplement? Yep. And would either one of those ever come out negative? In this problem, no, why not? Because x is acute. So if you know x is less than 90, you'll never get a negative answer. Questions on that? All right, so the other way that we can measure an angle is radians. So when I showed you guys this before, and you see that number below the one that's in degrees, that's a radian, negative 5.32 radians. And if you look at the word radian, kind of looks like another word from geometry. Yeah, it kind of looks like radius. And the way I'm going to explain to you what a radian looks like is using a shape that has a radius in it. And that shape would be a circle. So let's say we draw that picture. Okay, what I've drawn there is called a central angle. Reminder from geometry. That's when you draw an angle inside of a circle. The vertex is the center. And the two rays hit the edge of the circle here and there. Where those two rays hit the edge of the circle, I mark those points A and B. If you connect A to B, tracing along the perimeter of the circle, you get that shape in red, and that is called an arc. So I'm going to explain to you a special connection between a radian, a single radian, one radian, and the radius of the circle. If that angle is 1 radian, notice I didn't label it 1 and put like RAD on it. Whenever you write an angle in radians, it has no label. The only types of angles that have labels on them are ones that are in degrees. So that is 1 radian. If you draw that and you measure that angle and you make it exactly 1 radian, that picture's a little big, it's close, but it's probably a little off. If that picture is exactly 1 radian, then the length of that radius and the length of that arc will come out exactly the same. That's the connection between a radian and a radius. If angle ACB is exactly 1 radian, then the length of the arc and the size of the radius are equal. If that angle is more than 1 radian, then that arc will be bigger than the radius, which I think you can actually see in that picture. I think that angle is probably like 1.2 radian. It's a little bit bigger than 1 radian. So I think if you were to actually measure that arc, it would come out bigger than line segment CB. If that angle is smaller than 1 radian, then that arc will come out smaller than the radius. It's only if the angle is exactly 1 radian that the arc and the radius are equal. Any question on that picture? So it gives you kind of a visual. Doesn't necessarily tell you how to change between degrees and radians. Doesn't tell you that at all. But it gives you something you can kind of visualize to make 1 radian. Make the arc and the radius the same length. Okay, so how do we convert between radians and degrees? Well, it involves 2 steps. What number comes up a lot when you're dealing with a circle?
360.
Okay, degrees, 360 comes up a lot. Pi comes up a lot. Pi is going to be very important for converting between radians and degrees. If you want to convert from degrees to radians, there's 2 steps. One is to multiply by pi, and the second is to divide by 180. Now, converting the other way is very similar. In fact, it's so similar, sometimes you can mix this up. Anybody have a guess on how you can convert back?
By 180.
Multiply by 180. Yep.
And divide by pi.
And divide by pi. It's the reverse. So you want to be able to remember that. Well, the way we can remember it is like this. When you see the number 180, I want you to think degrees. Okay, I just want you to have that kind of connection in your head. See 180, think degrees. 180, think degrees. When you see the number pi, I want you to think radians. Okay, so if you associate the number pi with the word radians and the number 180 with the word degrees, all of that becomes kind of automatic. And you don't even really have to memorize which one is which. There's only 2 conversions you need to remember. One of them is pi over 180. The other one is 180 over pi. So let's try a few and see how we do. All right, so this one says convert to radians. That means it's in what unit now?
Degrees.
It's in degrees. Okay. To convert that, we're going to be multiplying by one of these 2 fractions. So let's make that a fraction first. How can you make 30 degrees a fraction? What could you do?
30 over 1.
Yeah, just put it over 1. All right. Now, let's think about what we need to multiply by. We are trying to convert two radians. We want degrees to cancel. Where is degrees in the first fraction? It's in the numerator. To cancel out something that's in the numerator, we would have to put something in the denominator. So degrees is going to go in the bottom. Radians, and again, the word radian, think of it as being invisible. Radian is in the top. What number did I say to always think of when you think degrees?
180.
So 180 goes in the bottom. And radians is in the top. What's the number we think of with radians? Pi. So to convert two radians, it's pi in the top, 180 in the bottom. And that causes the units of degrees to cancel. Okay, so we're going to multiply, but we can reduce first. What number goes into 30 and 180? Biggest number. 30. How many times does 30 go into 30? How many times does 30 go into 180?
6.
So now multiply straight across. What's 1 times pi? Pi. And 1 times 6? 6. That is how you write 30 degrees in radians. And I can show you. Right there. 30 degrees is pi over 6. You'll notice some of them have fractions with pi, but most of them just have decimals, if you just pick random ones. Anything that's a multiple of 30 or 45, you will generally see written as a multiple of pi. Like that one, 1/6 pi, or pi over 6. Let's try this one. Okay, converting two radians, and we want degrees to disappear. So where would degrees go? In the bottom. What number goes with degrees?
180.
And that means what's in the top? And what number goes into both of those?
45.
How many times does 45 go into 180?
4.
4? And what are you left with?
Pi for 30.
Pi over 4. Let's check it. Let's go to 45 degrees. Pi over 4. All right, let's try another one. Let's try 60 degrees. Now, here's a quick way to think about it. How does 30 compare to 60? That's half of it, right? So 60, how does 60 compare to 30? It's double. How much was 30?
6. 1.
How much was 30 degrees in radians?
Oh, pi over 6.
Pi over 6. So how much do you think 60 will be?
Pi over 3.
Yeah, it's going to double it to 2 pi over 6, which would be pi over 3. So once you know some of the basic ones, you can do the other ones faster. But let's say you didn't know 30. Let's do it from scratch. Multiply by pi. Divide by 180. How many times does 60 go into itself? How many times does it go into 180?
3.
And you get pi divided by 3. So like if you asked me what 120 was, I would say 2 pi over 3, because it's double 60. How about 90? Anybody see an angle up here that would help us to get 90? Okay, yeah, 45. How does 90 compare to 45?
It's 5. Or it's double.
It's double it. So what do we get for 45? So what do you get if you double that?
2 pi over 4.
2 pi over 4, which is pi over 2. And again, if you didn't know that, you could go back through and do it all over. But let's say you knew 30, but you didn't know 45. What would you do to pi over 6?
3 pi over 6.
3 pi over 6,
Yeah.
which is pi over 2 again. All right, so there's lots of different ways you can convert once you start to know a few things. All right, convert to degrees. All right, so now next to pi, it's invisible, but what word is there? Radians. Okay, radians is next to pi. We want radians to disappear. So where is radians going to go in the green fraction? It's going to go in the denominator, RAD. What number do we always connect with radians when we're converting? Pi. So pi radians in the bottom. What about the top? 180 degrees. So the radians cancels, that's invisible. The pi cancels. And is there anything I can reduce?
180 and 2.
Yep, 2 goes in one time. 2 goes into 180 90 times. And what would you be left with?
3 times 9.
3 times 90.
270 degrees.
270. And you need to put the degree symbol. If you don't put the degree symbol, what would that be?
Radian.
That would be 270 radians. Yep. All right. Well, this one we could kind of figure out by looking at the work we already have. We know pi over 3 is 60. This is double pi over 3.
120.
So it should be 120, but since it's only the second one we've done, let's practice it the same way we did the first one. All right. What goes in the bottom?
Pi.
Pi. What goes in the top?
180.
180 degrees. Pi cancels. Radians cancel. And how many times does 3 go into 180?
60.
60. And what's 2 times 60 degrees?
180 degrees. Or 120 degrees.
120 degrees. There you go. All right. Let's see if we can figure out C a little bit more intelligently looking at something we've already done. What angle or what problem, A, B, C, would help you figure out this one?
B.
Which one?
B.
B, yeah. This is B, pi over 4, times how much?
5.
5. So pi over 4 is how much?
45 degrees.
So it's 45 degrees times 5. If you didn't already know that, that's fine. You could go through and do it like we did A and B. What's 45 times 5? 225. D, we don't really have one that would easily help us with that. 7 pi over 12. What number goes into both 12 and 180?
6.
Yeah, we could do 6. 6 goes into 12 how many times?
12.
You could do 12.
And how many times does 6 go into 180? 30. But now, since we can reduce again, we probably could have picked a bigger number to start with. 2 and 30, what number goes into both?
2.
2. So what are we left with to figure out?
7 times 15 degrees.
7 times 15 degrees. Which is how much?
105.
105. Yep. Okay. So that's converting radians to degrees and degrees to radians. exact answers. Let's try this one. This time it says round to 2 decimal places. We're converting from degrees to radians. What's going to go in the bottom? Yep.
Degrees.
180 degrees in the bottom. So that'll cancel out degrees in the top. And what goes in the top of the numerator for the green fraction? Pi. Now, yeah, you could reduce it. I mean, I guess if you want to reduce by 10, just so you have less to type in the calculator. But we're typing it in on the calculator. So reducing it to its simplest form is not important. Okay. Somebody kind of guide me. How do you think I'm going to type that in?
500 times.
So I'm just going to do 50 since I canceled the 0.
Is there a pi symbol?
50 times pi in parentheses.
Right. You want to do the pi symbol. You don't want to do 3.14. Okay, so always use the pi button.
That's in parentheses.
Yeah, with order of operations, it would handle it correctly. You don't have to, but if you want to, you can. If you can figure it out.
Oh yeah, 5 times 50.
Okay, so 50 pi divided by
180.
yeah 18 because I canceled the 0. That's 8.73. Any label that I need to put on that?
No.
No. Okay, do not put a label. Okay, so 500 degrees is 8.73 radians. All right. How about, do I have another one of those? All right, let's do negative 200. All right, what would we multiply by? Pi over 180. Again, if you just want to cross off those zeros, you can. When you type it in, negative 20 pi divided by 18. That's negative 3.49 radians. Any question on that one? All right, let's do one more. Do it back on this side, though. This one I want to convert it. Actually, you know what? I'm going to save that one for the end. We'll do one more, but we'll save it for the end. Okay, find the degree measure. I'll do it as the last problem here. 3 radians. And again, we got to get used to not seeing radians there. RAD, it's invisible. What's going to go in the top? 180 degrees. And in the bottom? Pi.
Invisible radian.
And what is it? Pi what?
Invisible radian.
Radians. We don't write it, but we should understand it's radians. Okay. What's, if we multiply straight across, what's 3 times 180?
360.
180 times 2 is 360.
180 times 3.
180 times 3.
540.
540.
Okay.
So 540 divided by pi. What would you write down rounded to 2 decimal places?
171.89.
171.89. Now, if you divide by 3.14, that's a different answer. That's 0.97. That's quite a bit different than 0.89. 89 versus 97. Okay. Any question on that one? Not worried about that one. Let's do one more. So we'll call this example 7. If it doesn't say round, then you always leave it exact. convert 360 degrees to radians. Okay. What would we multiply by to convert that to radians?
Pi over 180 degrees.
Pi over 180.
Wouldn't it just be 1?
And what goes into both 180 and 360?
180.
180. How many times does 180 go into 180?
Once.
And into 360?
Twice.
Twice. So what do you get?
2 pi.
2 pi. And that's an important one to remember. 360 degrees is one revolution on a circle, and that is equivalent to 2 pi radians. About 6.28 if you wrote it as a decimal. So how much would 2 revolutions be? It would be 4 pi. Yeah. It would be 4 pi. Okay. How about 2.5 revolutions? 5 pi, because that would bring you over. There's 2.5, and now you're at 5 pi. All right. So any questions on converting? Well, everything we did. Converting degrees and radians is the most important, but then also stuff about angles. So the homework, we did lots of little things. Okay, classifying if an angle is acute, obtuse, complementary, supplementary, finding coterminal angles, convert between degrees and radians exact, convert between degrees and radians decimal, radians and degrees exact, radians and degrees decimal. So there's a little bit of everything we did. Okay, so homework is on 323, and we'll take a look at that tomorrow. And just a reminder, I will be after school on Wednesday for extra help.
Can you send me a manual extra credit for this week?
The extra credit?
There is none. It's for overshot week.
Yeah, the extra credit, next extra credit will be on this material, and it would be due the Monday you come back
So like after
from
vacation.
academic. Yeah, so after vacation.